Hello everyone, my name is Carlos Quintana and I'm here to talk about the paper called Methodology for Learning Multimodal Instructions in the Context of Human-Robot Interaction Using Machine Learning. So this is the presentation's outline. I'm going to start with a motivation and a little bit of context. After that I'm going to show you our proposed methodology. I'm going to show you also experiments, results, conclusions, and finally references. So let's start with motivation. The main motivation in this project is in the field of human-robot interaction, or HRI. The main idea, is to provide the robots with the tools to be able to communicate efficiently and in a natural way with humans, so that humans and robots can collaborate to perform tasks. In this example here, we can see a picture where a robot is collaborating with the human to perform a simple task, such as, in this case, moving this table from one place to another. In the general case, we want the robots to be able to efficiently communicate with humans in a very natural way. So this is the problem that we're going to be solving here. So in the context of HRI, suppose that we have the robot here on the right side, but we also have the human here, which we're going to be calling the user. So the human wants to issue an instruction, and the human wants the robot to be able to correctly identify such instruction, and later execute an action related to such instruction. In this specific case, instruction issued by the human is going to be it's going to have two outputs from the human, meaning two inputs to the robot. On one hand, the human is going to be given instruction as a spoken command, so it's going to tell the robot what the human wants, but at the same time the human is going to be performing a body gesture related to the specific instruction that the human is providing to the robot. So one instruction is composed of two specific outputs from the human: the audio or voice command and the body gesture performed by the human. We want the robot to be able to correctly identify the instruction and later execute some action related to such instruction. This is some of the related work, some of the works that are similar to ours. Some of them are similar in the way that they use specific sensor devices, such as the Kinect, to automatically recognize body gestures from the human. However, most of them are different because they only use one type of input. In our project, as I mentioned before, we want the robot to be able to use two types of inputs, and that's what we call a multimodal input. The last work is similar because they actually use multimodal human-robot interaction. They use body gesture and voice classifiers, but they are most interested in the model selection process for the classifiers using combined kernels. Okay, so I'm gonna go straight to our methodology. This is the general architecture of our solution. We have the robot here, and we have the user here, and we're gonna be using a specific sensor. In this case, the Kinect. The Kinect is going to provide us with both type of inputs. In this case, the Kinect is gonna be able to capture the body gesture performed by the human, but also the voice command or the spoken instruction given by the human using the microphones. These modules here, motion detection and voice activity detection, are simple modules that are going to be in charge of capturing or detecting whether there is an intention of the human to provide the instruction. So just to give an example, the voice activity detection module is going to be sensing the background noise level, and every time there are voice activity different than the background noise level, is going to capture data. The raw data coming from the motion detection module and the voice activity detection module are going to be the inputs to these two modules called feature extraction modules. So we're going to have to extract features or meaningful information from the raw data for the motion detection, but also for the voice activity detection. I'm going to show you later how are these composed. The output of these two modules are going to be the features, meaningful features that will describe the instruction, the voice instruction and the body gesture instruction. And they're going to be inputs to the multimodal classifier. The multimodal classifier, as you can see here, is composed of two unimodal classifiers, one for the voice and one for the motion. Inside the multimodal classifier, we're going to have a decision module. This decision module is going to be in charge of taking the output of each unimodal classifier and merge them together into one specific multimodal output. This output is communicated to the robot, and I'm going to show you later that the robot has the opportunity to ask to the user for feedback if the robot is not certain enough of the instruction that has been detected. The user can provide such feedback, and this feedback can be used to strengthen the multimodal classifier. So in the next sections, I'm going to show you a little bit about the feature extraction modules and specifically the multimodal classifier. First, I'm going to show you a little bit about the format of the inputs that we are capturing with the KeyNet. So on one hand, we have the body gesture. The body gesture is going to be three-dimensional data points that indicate the spatial coordinates of certain human body joints. So we have chosen certain human body joints that we believe that will help in detecting or identifying the body gestures, and we have a sample rate of 30 frames per second. On the other hand, we have the audio input, which is only a digital representation of the voice command. It's going to be the output of the 24-bit analog to digital converter of the KeyNet, and it's at 16 kilohertz. Okay, so I'm going to start talking about the gesture detection, the feature extraction for the motion detection. So the first thing that we want to do with motion is we want to normalize a gesture independently of the user that performs the gesture. So imagine that here in the top left, in this figure, this is a gesture performed by one user, and for the sampling rate we could have n's of 1 samples. On the top right we have the same gesture performed by a different user. So because it's a different user, we're going to have a different number of samples, in this case n sub 2. So the first thing that we want to do is to perform a subsampling process where we take equally spaced samples from this original gesture, and we normalize it to m samples. So regardless of the user that performed the action or the gesture, we're going to have at the end m samples that represent the specific gesture independently of the user. So that's the first thing that the feature extraction module performs. The second thing is, remember that for the motion we have three-dimensional coordinates extracted by the KeyNet for some human body joints. So imagine that this blue square here is the current sample. The green circles represent the three-dimensional coordinates of certain human body joints, and this is the sample in time t. The blue square on the right is going to be the position or the coordinates of the human body joints, the same human body joints, but in sample t plus 1, in time t plus 1. So we're not really interested in the absolute values of the coordinates to identify a gesture, but notice that it is most important for us. It provides us more information. How the spatial coordinates change from frame to frame to be able to identify a gesture. So in order to represent one body gesture, what we have done is we have created a sample as the difference between consecutive samples in time. So for instance, you can see that we're going to represent these spatial coordinates as the difference or the derivative between the sample in time t+1 and the sample in time t. In this way, we have the gesture detection features. On the other hand, we have the feature extraction for the voice instructions. And what I'm showing here in this slide is just a block diagram of what is called the male frequency cepstral coefficients. These are a set of coefficients that, according to the literature that we have reviewed, are meaningful to extract important information from the audio signal. So this is the digital representation of the audio signal, and this audio signal goes through a different type of transform and computations that finally allowed us to compute the male frequency cepstral coefficients. So we're going to represent one spoken command with a set of features, a set of coefficients. Okay, so let's talk about the classifier now. So on one hand, we have the voice features that are inputs to the voice classifier, and then we also have the motion features that are input to the motion classifier. Remember that these two classifiers output a label, an identified instruction, and these labels go into the decision model, who finally decides which instruction has been detected. So before going into the details of each classifier, I want to talk about the two different functions that are performed by our classifier. So on the left, we have what we call the training function. So our classifier will begin performing in training function. At the very beginning of the interaction between the human and the robot doesn't know the instructions that the human will provide. So the robot will start in training function for the classifier. So in the training function, the human is going to demonstrate, is going to show the type of instructions that we'll be providing to the robot. With this information, the robot will build an instructions database, and this instruction database will be used in a training process to create a classification model. So we're going to create a model that allows us to classify between instructions provided by the user. After that, the robot can be performing in interaction function. So here on the right, you can see the steps of the basic interaction function for the classifier. So in the interaction function, we assume that the robot already knows the type of instructions that this specific user can provide, and what the human wants is to provide one of the instructions, and the human wants the robot to perform an action after the identification of such instructions. So there is a user sample, which is an instruction. It goes into the classification model that it already exists since we are assuming that there has been a training process already happened. Then there is a response to the user from the robot, and there is a user feedback reception. The robot can ask for feedback if necessary. We can incorporate such a new sample into the database, and we can call the training function. So we can strengthen the classification model. So this is our proposed architecture for the multi-class classifier. So both the voice classifier and the motion classifier, they're both built in this way. So I'm going to show you this architecture. So remember that the inputs here are features that could be motion or they could be body, audio, voice classifier, instructions, and these features are inputs into an ensemble of one class classifiers. In this case, we are using one class for vector machines classifiers. Notice that we have one class SVN per instruction. So in this specific example, we can have n different instructions. Each one class support vector machine is going to be able to identify whether the input sample belongs to its own class or not. So at the output of each one class classifier, we're going to have whether the sample belongs or not to each class, and these outputs go into this output function. This output function is going to be in charge of merging or combining all those outputs to create just one final output. Notice that this architecture allowed us to create new instructions or new classes without the need of retraining the whole multi-class classifier. For a new class, the only thing we have to do is to create one new one class for vector machine classifier and include that into the output function. Okay, so now that we have the unimodal multi-class voice classifier and motion classifier, the output of those classifiers goes into the decision model. The decision model is the one in charge of merging together the output of the voice and the motion classifier. So the voice classifier could say this sample belongs to class number 3, for example, and the motion classifier could say this sample belongs to class number 2. So the decision model is in charge of saying what the final output is. So we have implemented a very simple decision model function, which is the one we're showing right here. And it's quite simple. So notice that if the voice classifier and the motion classifier agree on the identified instruction, so the class of the input sample, then the decision model will have nothing to decide. If they agree, if the labels assigned by both classifiers is the same, then that's going to be the output of the decision model. However, if the voice classifier and the motion classifier disagree, meaning that the assigned labels of both classifiers are different, and the confidence value of the video or the motion classifier is greater than the confidence value of the audio classifier by certain threshold, then the output is going to be the one, the label assigned by the video or the motion classifier. Similar to that, if the assigns are different, if the classifiers disagree, and the audio classifier has a higher confidence by certain threshold value, then we're going to say that the output is the one assigned by the audio classifier. And we're going to have a last one last thing, and is if they disagree, but the difference in confidences is not high enough, then we're gonna say that we're not sure of the answer. So the robot will say, I'm sorry, but I did not understand such instruction. So we have created a set of experiments in the context of human-robot interaction. So remember that we have a user that is interacting with the robots in two ways. The first way is the human has to show the robot the instructions and perform several repetitions so that the robot can learn and create the multimodal classifier, the model. And after that, after the robot has been trained, then the user will perform in interaction mode, which is basically it will issue instructions and is going to expect the robot to understand what the user said. Okay, so in the experiments we use a Darwin OP robot. We have the processing system, which is a laptop, a computer, The keynet is connected to the computer, and the computer is running the application for data capturing, and also the multi-class classifier is implemented into the computer. So here we can see this is the setup for the experiment. So we have the robot, we have the keynet, and we have the computer, and here you can see a print screen of the data capturing and classifying of the instructions. What we have done is we have implemented 5 different instructions in 4 different users. The instructions, remember, that are composed of a spoken command, which is an audio, words in Spanish, and a body gesture. So for example, here the users say hello in Spanish and perform greetings with the right hand. Another example is, for example, the users say right in Spanish and move their head to the right. The robot should be able to identify such instructions. Okay, so here we can see some of the most important results. We're going to show here only for 2 different users. So the top figures show for user number 1 on the left, user number 2 on the right, and what we can see here is the number of accumulated errors on the vertical axis, and the number of interactions on the horizontal axis. So each user is interacting 100 times with the robot, and the straight red line that you can see here is just a straight line with -1 slope. What we can see here on the lines, the color lines, are just the number of errors during the interaction for the different instructions or classes. So what we can learn from this figure is that it shows that our system is actually learning. You can see that at the beginning all the figures, all the lines are very close to our baseline, the straight line, and the reason for that is because every time the human interacts with the robot, the robot doesn't know anything at the beginning, and so it will make constantly mistakes. The models are poor, and it's going to be making mistakes once and again. However, you can see that as interaction goes, as time goes, this accumulated number of error tends to flatten. This means that the robot is no longer making mistakes. So it means that it's correctly classifying the given instructions by the user, and it happens with both users in this case. On the bottom, we can see these two figures. We have the accumulated number of queries. So remember that the robot is able to ask for feedback, and it does so when the confidence values of the classifiers are too low. So notice that at the beginning of the interaction, for both users, the robot is going to ask for a lot of feedback. That's consistent, since we assume that the confidence of the classifiers is low because it has very few training samples. However, in time, as in the interaction goes, this accumulated number of queries again tends to flatten or to saturate, and the reason is the same as above. The confidence value for the classifiers is higher, and so the robot doesn't have to ask for a lot of feedback after some time. In this plot, what we're showing is the generalization or error of the classifier for the two different users, and we're showing it here for different colors for each instruction. So we're only showing here 3 different instructions, namely hello, head, and right. What we can see here is that at the very beginning of the interaction, the size of the training set is very low because the robot doesn't know anything, and the generalization error is high. However, as the interaction goes, the size of the training set grows, and the generalization error tends to decrease for both users for the three instructions. So what we can see here is that effectively our classifiers, or our model, is learning. So I have a little video here that I want to show you with the experiments. So what we can see here is first the training function. So the user, the human user, is demonstrating the robot. The instruction in this case is just using her right hand and speaking. In this example, we have a different user, and the user is interacting with the robot again in the training function. So you can also see here in the bottom, the left bottom, the data capturing application, and we can see both type of inputs, the audio and the motion inputs. And finally, we can see the third user. In this final part of the video, we can see the user that is already interacting with the robot. So the user is no longer in training function, but in interacting function. And so the user is showing the instructions provided by the previous users to the robot, and is expecting the robot to perform an action. In this case, for example, lifting the robot's arm. Finally, these are the conclusions. So we have built an instruction learning system that allows a human to control or receive help from a robot in a natural way. The system exploits multimodal inputs to improve the learning procedure. The overall learning architecture is based on an ensemble of one class of 4 vector machines that allows the system to improve its model without complete retraining. And the system includes a feedback mechanism from the robot when the confidence of the classification is relatively low. Thank you very much.